some of you, and I got the impression that I got lost in my arguments towards the end of the class, and I want to make sure that that was clear. And then we are going to start discussing a very simple model that we are going to use to develop the techniques that I want to discuss with you. So remember that we were introducing this system of interacting bacteria, and the result that we were interested in trying to understand was this experimental result that you have in the screen. That was basically data collected for interactions between these two types of bacteria, one that was secreting a molecule that was able to kill the other. And what these researchers found experimentally is that when you place these two strains of bacteria in a well-mixed environment, there is biostability. So basically there is a threshold in the initial population size of the producing bacteria below which she is not able to proliferate in the population. And that threshold disappears when they put bacteria in the spatially structured population. Remember that this was interesting biologically because the fact that we require a minimum population size for this new behavior to proliferate in a population is telling us that it's very unlikely that it will appear because we need a very big initial seed, right? We need to put a lot of things before for this behavior to start. So we developed this very simple model that was describing the global density of each of the bacterial strains in the population, and we had found the issue that whenever we have the interaction terms or the density dependent terms, because they depend on how the population is structured, we had the description of the system combining global variables and local variables. And the local variables are really hard to handle. So we came up with this well-mixed approximation that we call, that basically says that I'm not going to care about these conditional probabilities. All I'm going to say is that the probability of finding an empty place next to a place occupied by one bacteria is equal to the density of 0. So I'm completely killing spatial correlations in the population, and using that I arrive to a closed system of differential equations based on global densities. Then I think that things got a little bit confusing when I started analyzing this system, and that's why I want to use 15-20 minutes to do it slowly and to make sure that we are all in the same place. What I was telling you is that once I have the dynamics for these two population sizes or population densities, usually these dynamical systems, they are nonlinear, they are hard to solve. Analytically, most of the times it's going to be impossible. So what we try to do is we try to find the points towards which this dynamics is going to be, the equilibrium points. And then we try to understand which of them are stable and which of them are unstable. And to do that, the technique that we usually do is to equate these two equations to 0 and try to find the conditions for which each of these variables is equal to 0. In our case, rho 1 and rho 2. Doing that, you find these expressions for the nucleons. And we're going to analyze them very, very slowly to make sure that all of us understand how we analyze these two-dimensional dynamical systems, okay? Perfect. So yesterday I started saying high cost, low cost, and I understand there was some confusion. I was introducing that very, very, very fast. The way I'm going to define the cost is by the difference between the growth rate of the strain that does not produce chemicals and the strain that produces chemicals. Remember that we had this condition. So the difference between these two growth rates is the amount of energy that I need to spend in this behavior, and therefore is the cost of that behavior. So if, for instance, I eat 4 publications and I'm able to allocate the 4 of them to reproduce, to grow, and if I want to express this behavior, I need to invest 1 pound acacia into producing toxins and 3 into growing, then my cost is going to be 1. 4 minus 3 is equal to 1. That is the definition that I'm going to do for the cost. And then we had this efficiency or effectiveness of the killing behavior that basically was telling us how strong my chemicals are. So how fast I kill my neighbors when I invest into this behavior. So how toxic I am. in the good sense, not in the bad sense. Great. So yesterday I distinguished these two regimes, high cost and low effectiveness, high cost and low effectiveness, and low cost and high effectiveness, and we saw that the model had different behaviors. And we're going to see why slowly to make sure that we are all on the same page, okay? So the first thing that I was doing, and the first thing that we need to do, is we need to define the space in which we are going to put the two densities. And here, of course, you can put wherever you want in each of the axes. I'm choosing just row 2 and row 1 in this way. And here I can plot the null lines. I'm going to try to use yellow and blue. Let's see how it goes. So I'm going to draw in blue the curves at which row dot 1 is equal to 0. Row 1 dot is equal to 0. So row 1 equal to 0 is this null line. Well, blue is almost white. And I'm going to use yellow for the other one. So row 2 equal to 0. This is clear. This is regardless of my parameters. Perfect. Now I have these two other expressions. Here. So when row 1 is equal to 0, the point at which these two lines are going to intersect this axis here is 1 minus delta divided by beta 1 and 1 minus delta divided by beta 2. Correct? And I know that beta 2 is higher than beta 1. That's a universal truth because of the constraints of my model. Which means that if beta 2 is larger, this number is smaller than this one, and therefore this one is closer to 1 than this one. So this one is bigger. Perfect. So here I have 1 minus delta beta 2, if this is 1, and here I have 1 minus delta divided by beta 1. What is interesting now, the important point, is that the slope of this null line is always 1. But this one depends on gamma. When gamma is very, very small, this slope is almost 1. And therefore, these two lines are going to be almost parallel, correct? And there is no way that they will cross, by definition of what a parallel line is. Sorry, I am already mixing the colors. This one was for row 2, and this one was for row 1. Nothing very fancy so far. And I told you, the points towards which my dynamics is going to be are the points in which both variables don't move. The dynamics of both variables is frozen, which means the points where row dot 1 and row dot 2 are equal to 0 simultaneously. That means the points where blue and yellow cross. Blue and yellow cross. This and this. So these are all the potential equilibrium states of my system when gamma is small. Now let's discuss a little bit why gamma small is equivalent to C small, to beta 2 and beta 1 being very, very similar. If I fix a large gamma, whenever I take beta 2 closer to beta 1, the meaning of taking beta 2 closer to beta 1 means making beta 2 smaller, right? I fix beta 1, and I make beta 2 smaller, 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 smaller. So basically, the slope of this line is again tending to 1, right? Because it's in the other side of the slope. So that's why these two limits are equivalent, okay? Perfect. Now I have fixed points here, and I need to understand the stability of them. How many of you have done this before? Okay, less than half. So the rest of you didn't get anything yesterday from the plots I was showing. Perfect, great, happy that we are doing this now. These are the kind of things that I would like you to tell me. Yesterday I talked to 3 of you and I realized, but if that happens for the majority of you, we go back, okay? Perfect. So I have 2 points here. And these lines are lines where rho2 dot is equal to 0, rho1 dot is equal to 0. Remember my color code. This means that whenever I cross this line, the sign of the derivative of rho2 and rho1 has to change the sign, right? Because they are continuous. So what I'm going to do is I have 0, 0, which by the way is another potential equilibrium state that I was not mentioning. And I know that beta 2 and beta 1 are positive, right? So if I am departing from 0, the derivative of rho2 and rho1 here, they have to be positive, right? Rho2 has to increase because I have no bacteria and I throw in a little bit, and rho1 has to increase as well. The point is that now, whenever I cross the rho1 nucline, the derivative of rho2 is not going to change, but the one for rho1 is going to change. And if I repeat the same every time I cross every nucline, and I change only the sign of the variable to which that nucline belongs, I start understanding what are the directions at which rho1 and rho2 simultaneously move into this phase space that I am constructing. So here, if rho1 increases and rho2 increases, if I plot rho1 and rho2 as a parametric function of t, they are going to go in this direction. If here they go like this, they're going to go in this direction, and if you reconstruct with some imagination or with software, then you see that you will get this kind of arrows. So these arrows with these slopes is basically what I am here qualitatively reconstructing with my geometrical arguments. Okay? So this is the basis. The more you practice, the more you will be able to do this fast. But this is the idea. You draw the null lines. These are the lines at which the derivatives are equal to 0. And then with the knowledge that you have from their system, you start reconstructing the dynamics of this system. When you work with systems like this, ecological systems, the trick that I always use is 0, 0. Here it always goes, both of them go up. And then from there, you start crossing null lines, and you do it. This is, you can do this kind of plots with Mathematica, with Python, or with anything that you are able to use. Perfect. So this basically means that if my dynamics is going to go in this direction, this is going to be an unstable fixed point. Here, whenever I cross the rho1, I go in this direction. So basically, you already see that this fixed point is unstable, and you basically, whenever you start, you always go to the exclusion of the producing bacteria and dominance of the non-producing bacteria, which is the scenario that we don't find in the experiments, because it doesn't make any sense that I invest into killing someone into a behavior that is aimed to kill that doesn't kill. That's not evolutionarily stable. Perfect. And this is the result that we got. Now, why do I have a qualitatively different result when I increase gamma? It's very simple. When I increase gamma, this slope increases. And all I am doing is to shift this line in a way that at some point it will cross the other null line. So I am creating a new fixed point because I am creating a new crossing point between the blue and the yellow null line. If you repeat the same, changing the sign of the derivatives, what you will find is that this point that we call saddle node has a very interesting behavior because it is dividing the phase space into two different regions. One that is a basin of attraction for this fixed point, so everything that I put in this region is going to be attracted by this fixed point, and another one that is going to be the basing of attraction of this other fixed point. So by creating this new equilibrium, this one gains stability, and this one keeps hers, and therefore what I'm doing is just creating this by stability, by increasing gamma, okay? Yes?
Could you please maybe recap what, how did we conclude that that point that you painted in white is an attractor?
Which one? This one?
Yeah, this one.
When in the case where both are parallel? Yes, all I do is, I know this one is a fixed point, right? And I know it's unstable because the 0, 0, the state in which I don't have any bacteria, if they grow with positive rates, as soon as I put a little bit, they will grow. Because, okay. So then what I know is that the derivative of rho 1 in a small neighborhood of this point is going to be positive, right? Rho 1 is going to increase. Sorry, this is rho 2. Rho 2 is going to increase, and rho 1 is going to increase as well. And then all I have to do is I need to define, I need to focus on one of my variables, let's say rho 1 here, and every time I cross a null line, the definition of the null line is the line where the derivative of 1 is equal to 0. So if here is positive, here is 0, then if it's continuous, here is negative. Right? Because here it's equal to 0. Well, sorry, now it's a bit confusing because I move it. But basically, every time that you move in this space, whenever you cross a frontier where this derivative is equal to 0, you change the sign. That's what I'm doing here. Here it goes to the right. Whenever I cross the line that is the red one, goes to the left. Sorry, it's the red one, it goes to the left. And the same, it goes up, and when I go to the black, when I cross the back, it goes down, and then you basically interpolate and you get a sketch of how these curves are going to go into this space.
Mm-hmm. Because when I look at the red dashed line, what I see is that some errors are actually passing through it without
of course
changing sign.
Of course, they cross it. The thing is that you see that when you cross the red line, so here is going, let me see. Here is going, it's kind of going to the right, and when I cross the red one, it's going to the left, right? The parabola is changing. Because here it's moving this way in the x direction, and in the y direction it's moving this way. I mean, if you go to the extreme epsilon close to the line, maybe it's not because of the resolution in the lines, and one is on top of the other. But whenever you cross the null line of one of the variables, you change the sign of the derivative, right?
It's not intuitive because it could be just an inflection point.
It could be just, huh?
These nuclides could be just an inflection point.
What do you mean by an inflection point?
We're a saddle point. Thank you.
Yeah, this is what is here. This is a saddle point of the dynamics because you have.
Yeah.
Because of how, and here it's because of the resolution of the lines, but because of how the directions of the flow change in the neighborhood of this point, it's when you create this separation of the phase diagram. But you need to go region by region, left to the red line, right to the red line, up, down, and then you reconstruct the directions. Okay? We are going to do that in one dimension.
Okay.
Maybe it's
Thanks.
It's easier. In any case, this is the idea. And then whenever I am in this case, everything that is in the basing of attraction of this fixed point goes to this fixed point, and everything that is in the basing of attraction of these 6 points go to the other fixed point. And when I integrate curves over time, these are the plots that yesterday were mixed, I get that when the initial density of producing cells is very small, they go extinct. This is the case of an initial condition that starts here. But when I increase the initial density, I go to the basing of attraction of the other point, and I get dominance of the producing cells. Okay? And just the final bit, what I showed you yesterday is that we can, of course, depending on the cost And this effectiveness, we can divide the outcome into by stability or stability, depending on the existence of this fixed point, basically. And when effectiveness is low, you see that this is always monostable. And as you increase effectiveness, you start creating this bistable region. What is interesting about the spatial case, that is what we're going to study now, is that when I run my simulations in a lattice, and the initial density and the efficiency is low, or the cost is high, nothing changes. The non-producers are still winning, and they dominate. But if I go now to the case where I had bistability before, and I run numerical simulations with a very small density of producers, they are able to win. So they are able to violate the bistability. Somehow now it's the dominance of one is monostable when I have a space. That is the important point. The important point is that the initial density of my producer cells in this case, 0.54321, 0.001, it's way smaller than the one I had before, 0.2. Here they died, but here they win. And what the simulations tell us is that this is because of the way they are structured in space, because they are coarsening from an initial drop. Okay? Perfect. More clear now? Okay, well, I don't know.
So the simulations are done by using the rules, right?
Yes, this is a Monte Carlo simulation.
Okay.
This is an cellular automata Monte Carlo simulation where I have all my white places are empty. White means empty, gray means non-producer, and black means producer. I put a drop, and I look at the evolution of the system. Okay? Of course, if the drop is very, very small, you may have fluctuations that kill the drop, and finite size effects that maybe those of you familiar with statistical mechanics already are thinking of. So the interesting point is that if we want to recover this behavior, we somehow need to keep track of the spatial correlations. This approximation is very bad. If I want to try to explain that result, this one is very, very bad. In the papers that you have in the drive, they go beyond this approximation for this complicated system, but it's a very, conceptually it's not hard, but in terms of doing the algebra, it's hard. Why? Because I have a lot of conditional probabilities, I have 3 variables, and I have a lot of algebra to do, basically. My system is high, it's large, and it's a little bit tedious to handle. So what we are going to do is to introduce a very simple model, the contact process, where we are going to be able to develop higher order corrections to the well-mixed approximation. We are going to solve it, and we are going to see how simulations, well-mixed approximations, and approximations that account for spatial correlations agree and disagree in different regions of the parameter space. Okay? Great. So the model that I'm going to introduce, I'm going to work with it in 1 dimension, of course. But I'm going to tell you which are the points that you need, in which parts of all the calculations that we are going to develop, you need to be careful if it's higher dimensions. It's basically when you count the spatial correlations. Okay? Great. So how many of you have seen the contact process before? Okay, good. So the contact process is probably I don't know if the simplest, but at least it's the first one that people usually learn when they start studying non-equilibrium statistical mechanics. It's a stochastic process that we are going to define in a 1D regular lattice. This means that my space is going to be a line of different places, and it's going to be important if you want to do numerical simulations. Usually you account for periodic boundary conditions, which means that the right of this one is this one here. Okay? Perfect. The number of processes that we are going to have is very small. We are just going to have birth and death. Death is always the good one, the easy one. Is the easy one. Basically, individuals that are in each of these nodes will die at a rate delta. And the birth is going to be a little bit more tricky, of course. So basically, each of these nodes can be in a state that I'm going to call plus and 0, occupied or empty. Occupied places go to empty at a rate delta. And of course, for the birth, I will have that occupied places, when they are next to empty ones, they can infect them at a rate that it's going to be B. I'm going to call it B divided by, because I'm in 1 dimensions, divided by 2. So basically this means that empty places, they are going to become occupied at a rate that is equal to B, which is the rate at which this guy is going to create a seed, divided by 2, because this guy in principle can infect the right or the left. Okay? So the maximum rate at which this place is going to be infected is B, and it's going to happen whenever the both neighbors are occupied. Clear? Good. I think I broke something. So we have very simple rules, stochastic rules. The first thing we can do, like always, is to do simulations in the computer. Doing simulations in the computer for this model, it's not trivial. If you want to do them properly and you need to find critical points properly, it's not trivial. There are techniques to calculate when the population is going to go extinct and when it's going to go to a fixed point that is not extinction. It's not as easy as I'm going to show it to you now. I'm going to show you results, and I'm going to tell you what I did, and I'm going to tell you the right way of doing that. But we are not going to do that here because it would be like a full course doing that. And also, I think it's been like 12 years since I did that the last time. But basically, we have a lattice. We have stochastic rules. We can just run an algorithm that goes through time. I define, let's say, an initial configuration of my lattice. And then in every time step, I need to choose if I have birth, if I have death. Let's say this is the step 1. And then in the second step, I need to choose the node at which this event is going to happen. So the probability at which I'm going to have a birth that I'm going to define by P let's see how many of you are lost by this expression, is going to be this, which basically tells me that every occupied place can reproduce at a rate beta, at a rate B. Every occupied place can die at a rate delta. And therefore, the probability that I have a birth is the relative rate of birth divided by the total rate. Of course, I can simplify this, and this is what I get. And of course, the death probability is going to be 1 minus p. When you implement this in the computer, there are many ways of making this more efficient. You can think of discrete time, as I am thinking now. T is 1, t plus 1, t plus 2, t plus 3, because I don't care about the time. But if you care about the time, things like critical slowing down, relaxation time scales of the system, then you need to treat the actual rates, you need to treat the continuous time, and you need to do things in a more sophisticated way. For us now, this is going to be a kind of a cellular automata. We are only interested in the stationary states, and therefore I am not going to care too much about characteristic time scales here. Okay? Actually, I'm going to at some point rescale my time and take delta equal to 1 and measure everything in terms of the death rate. Okay? All I want you to understand now, and those of you that are going to be the afternoon in the ecology projects, you are going to implement a simulation like this, is that when you have these kind of rules, what you do is to throw a lot of coins and then choose what happens depending on the outcome of these coins. It is a very brute way of explaining it, but it's basically the core of all these algorithms. And then once you choose the place, then this configuration is going to update, and at some point is going to reach a stationary state that can be, we'll see now, can be extinction, or it can be persistence of the plus states, or wherever. I'm going to talk about population size a lot because that's my bias, but of course, this is a model that many people use for epidemic spreading. We saw it yesterday, for fires, for many, many things. Okay? At the end, this is a model that is very simple. It has a very characteristic symmetry, that is that it has one absorbing state. So whenever the dynamics goes to 0, it stays there. There's no way that fluctuations take it out from there, because there's no fluctuations basically in that state. And that gives this model like properties that it shares with any other model that has this kind of same symmetries. For us, it's going to be a population of trees, if you want, that put seeds in their neighbors if they are empty. If they are occupied, they don't. And it goes through time until it stabilizes in a population size. How many of you have calculated critical exponents for this model and things like that? No one? Ah, you don't know what you miss. I spent 3 years of my master's calculating the critical exponents of these kind of things. Anyway, yes. You want to know how to calculate the critical exponents?
It's a quick question. Why there's no over Q for the probability expression?
Where is not over what?
The B over Q.
B over 2. Yes,
Yeah.
good point. There is no B over 2 because what I'm doing is the probability that I have a reproduction event is the rate at which any occupied place in my system produces a seed, which is the number of trees times the rate at which each tree produces a seed, which is only B. Remember that the 2 comes when I look at the dynamics from the point of view of the empty place, because so imagine that you have a configuration like this. Let me keep the notation as it was. A configuration like this. What I'm telling you is that this tree, this plus, creates a seed with rate B. Correct?
Yeah.
And this also. This means that whenever this guy produces a seed, she has to decide, or whoever is in charge of deciding, whether the seed goes to the right or goes to the left. So the probability at which this 0 is going to become a plus is going to be the rate at which this neighbor produces a seed, B, divided by 2, because this guy has to go here, plus b divided by 2 because of the same argument, right? And this is equal to b. But if I have a configuration like this, the probability of the rate at which this 0 is becoming a plus is going to be only b divided by 2, right? Because I only have an occupied place. But the rate at which this tree produces a seed is always b, because this is an intrinsic property of the tree.
Okay, tricky, thank you.
Great. That's why you had to ask. Good question. I'm pretty sure many people had it and didn't ask. Great. So we can run simulations of these dynamics. Yes.
So if you select so if you select an event, right? Birth or death.
Yes.
Then you have to go back to the lattice, and then you have to select. I mean, I'm just wondering how this dynamic will work in the computer. So you have to check each lattice is occupied, and then it can give birth to a site nearby.
Yes.
So it goes like this, right? So if first you select an event,
Yes.
then you have to deal with the lattice.
Yes.
Ah, okay.
And that is not very efficient.
Uh-huh.
And that's why very often, if you want to optimize this, what you do is you already select, you create an auxiliary lattice that only has the occupied places, and you only select from the occupied places to avoid having a lot of zeros. And actually, and this is maybe a little bit technical, so those of you that don't follow it, don't worry a lot, but this process is so simple that you can map it to a process based on pairs. And that makes the simulation much more efficient, because you just track plus, plus, plus 0, 0, 0, and then you do the dynamics of that. That's explained in the book by Marro and Dickman that I told you yesterday. They show how you can map this to the dynamics of pairs and how that makes things much more simple and much more efficient. Once you have the abstraction to do the mapping, of course, no? So it's always saving computational time comes at the cost of thinking a bit more about the system, trying to find mappings that you can do and do the mapping, no?
And then you select the site randomly. Like
you select one place randomly, and then you select right or left randomly as well. If the place that you select is, the neighbor that you select is occupied, you just don't do anything. That's usually what you do, which is again another waste of time, no? So usually what you can do is you can choose only neighbors that have, only places that have neighbors empty, to make sure that you don't throw a coin and do nothing, right? The point is that when you do that, you need to be careful, because usually your time scale is changing as well. Because you need to, if you are interested in time scales, you need to take into account that in reality these nothings are happening, no? So when you do continuous time, that is easy, because you are basically have a characteristic time scale that changes, and it's fine. But when you do discrete time, you need to be a bit more careful. Yes. Yes. If it changes a lot the behavior of the system? Yeah. If the system is small, yes. If the system is small, things change a lot. With these kind of models, I don't have a very strong intuition. With continuous models, like PDEs, for instance, you remember Guillermo's talk yesterday when he was showing us the lattice simulation and then the PDEs. With those PDEs, usually you may have solutions that are stable, uniform solutions that are stable when you take boundary conditions to be periodic, and when they are not periodic, you can have patterns, for instance. Right? You can, if you're familiar with Fourier analysis, you can think in terms of Fourier, how you are cutting off modes when you put a periodic boundary condition, no? When your system is finite, no? But again, that's for continuous models. Here, I know they change, but I don't have so much intuition. I haven't done that much. Great. So what I can do now is I can run numerical simulations of my system. As I told you here, I already took delta equal to 1. So my control parameter, if you want, is going to be delta divided by B, which means the ratio between the death rate and the birth rate. The smaller this parameter is, the more productive my system is, the faster the birth versus the rate, and the other way around. So here I'm taking a very small ratio between death and birth. And as you see, I'm running simulations. Here I took, I think, Lattice to be 10,000 places. Periodic boundary conditions, 1D, and I think that was it. And basically, what you see is that I start with different initial densities, so basically different fractions of nodes occupied by a plus. And you see that my dynamics relaxes, and at the end it goes to the same stationary state. You see that it has some fluctuations, right? There's some noise here. In this case, they are not very, very strong because I'm taking 10,000 to be the size of my system. If your system is smaller, these fluctuations are bigger. And I can even go to very, very small densities, and you see that it takes longer, but at the end it goes to the same stationary state. So in principle, this is a kind of boring model. At least for this combination that I'm using, doesn't have stability. It's just a percolation process in which, depending on the ratio between birth and death, I percolate, the population percolates until reaching a given stationary size, right? And I'm using percolation on purpose because this model belongs to a universality class. Those of you that are more familiar with statistical mechanics, that is called directed percolation. Okay? Yes.
This limiting case of infinite time analytically, I mean, can we know what's the number that these curves are converging to?
Yeah, that is what I want to do the next 2 days. Yes. So basically, I mean, yes doesn't mean that we can. Yes means that we can try. But the dynamics is just one example. We can do different simulations. Basically, we can change B and just plot the density of occupied places in the stationary state as a function of my control parameter. And here you have the classical phase transition between a regime of the parameter space in which my population or my density of occupied sites, my density of trees, if you want, goes to a non-zero value. And then whenever my birth rate is very small, remember that this is 1 divided by B, then the population is not able to persist and it always dies. Right? So 2 very clear regimes. One in which the population persists, or the epidemic persists, or the memes persist, or wherever you want to do persist, and another regime in which it goes extinct. When I have an inverse of the birth rate that is 0.387 something, I have a critical point. I have a transition point. And this is the critical point for the one-dimensional contact process. You can do theory to calculate this critical point. Okay? We had some questions yesterday about the dimension. If I do this simulation in a 2-dimensional lattice, this is different. What is different? The phase transition is different. This point is going to shift, and the behavior of the system in this point is going to shift as well. If you calculate things like critical exponents and things like that, they change. They change with the dimension. Okay? Good. So simulations, pretty easy and useful. Now let's try to satisfy Lauro's curiosity of whether we can find the fixed points analytically or not. What is the first thing you would do? Any of you, not Lauro. What is the first thing that you would try to do? Good, yes. Which kind of equation? Well, now I have a system that is much simpler than the previous one, right? Now I only have occupied or empty. That means that now I can describe my system by the density of pluses or the density of zeros. And I, of course, know that they are equal to 1. So basically, I can write just an equation for rho plus, and I have everything. Let's try to write that equation. Anyone wants to try? No? Too shy yet? No? Okay. What is the first process that I have? Death. I'm going to already take delta equal to 1. So basically, they die at a rate 1. Birth. Let me make sure I keep the notation. Let's see what happens with the 2 now here. What is the birth term here? I need 1 occupied place to produce a seed, right? So basically the density of occupied places times the rate at which they produce seeds. And now, again, I have the same problem that I always have. Again, local density, global density. I am going to go a bit faster here. Well mixed. To what? I don't know who thought this morning broke it. We all agree on that. Here. Rho 0, perfect. This is we can say a modification of the logistic equation, right? It makes sense. At the end, the logistic equation is the same. If you think, like the mechanistic idea of this equation, it is the same. I have some animals that they are reproducing at a rate R, and then at some point they have some non-linearity limiting this, and then that makes them to saturate at a carrying capacity K. Of course, there is a very big difference, and I'm not saying nothing about the people that do this kind of equations, postulates them this way, but there is a very clear difference between writing this down or writing this down. In my opinion, it's a clear difference on the understanding that you get of the system, no? But fine. Actually, there is a very, there is a lot of, I don't know if books or papers, discussing how you can get to this equation from very, very different things, very different mechanisms, very different processes. They all lead to this equation for the mean number of animals, or the mean number of occupied places, the mean number of infected people. But the fluctuations are very, very different because of the way that you are defining the processes. And that changes things a lot, right? So in this case, for instance, just to give you an example, let me stop a little bit here because I think it's interesting to develop this intuition. Now I have my equation. This is equal to B rho plus 1 minus rho plus minus rho plus. You can rewrite this. This is not very. If you want, R. So if I do this very sketchy rearrangement of my equation, you see that the nonlinearity in this case, the intensity of the nonlinearity is weighted by B, no? So the carrying capacity is not arbitrary. It's B. It's modulated by B. Why? Because what is limiting the growth of my population, what is limiting my spreading process is size, is the space that I have available, right? And it makes sense that it cannot be anything else. This is 1 minus rho for a reason. Because it's the number of empty places. It's a space limitation, what is avoiding the infinite growth of the population. If you think on any other process that inhibits the replication, that inhibits the spreading, that is not related with the space, maybe, yeah, you can have here some, I don't know, some weighting, some encounter rate, let's say. Imagine that this is, I don't know, they eat each other. These are lions that are growing together and they are cannibal lions and they eat each other, or whatever. Or that they are competing for food in any way that is not space. Then you have here an encounter parameter, that it can be different to the available space. And then things are different. And the interpretation of the model is different. So that's why I think it's a little bit problematic to write down mean field equations or well-mixed equations, like the ones that we are writing now here, without understanding the limit of which process this well-mixed process is. But that is my personal opinion, that can be a little bit biased, because we've been now working for, I don't know, 8 or 10 years trying to relax well-mixed approximations in different systems. Good. So let's go back to the class. I have my equation, and this one is easy, no? Because it's one dimension. I can do the same that I did before, but now I don't have null clients. It's only points, and it's much easier. And actually, in this case, it's easy because I can solve it. No, I can say, well, this rho plus is equal to 0, or B1 minus rho plus is equal to 1, which means that rho plus is equal to 1 B minus 1. So what is well-mixed approximation is telling me is that the density of occupied places as a function of 1 divided by B is something like this. It's a line, right? This, if I plot together with the simulations, this is what I get. It's the same. We all agree that it's the same quantity, right? It's the density of occupied places. In one case, of course, sorry that I didn't give a lot of details on how I calculated this. The red points, what I have to do is I have to run my numerical simulation 10,000 times, and I calculate the means, and if I were a little bit less lazy, I would calculate error bars or variances and things like that. No, this is numerical simulations, numerical averages. A good trick is to put the points very big so they are bigger than the variance and you don't have to put error bars. Nah, I'm kidding. And then on top of that, we have the solution that I just got, the mean field, the well-mixed approximation. It's pretty bad, no? In principle. Why do you think it's bad? So are you surprised that it's bad in this direction? Like, let's say, I have, wow, I think someone got annoyed by me not changing the, so this is what we get, more or less. Well, I put a big system, so it's this. How many of you would be surprised if I show you something like this? Or how many of you don't, I don't know, you show me that, fine. Like, it's an honest question. How many of you were expecting that comparing my numerical simulation with this result would give me a higher density, sorry. How many of you were expecting that this analytical approximation would overestimate the numerical simulations? You were expecting that. How many more? 2, 3, 4? How many of you were expecting the other behavior? 1? How many of you were not expecting anything and just no intuition? No, it's a fair question. How many of you didn't build intuition? That's fine. Anyone wants to tell me based on what they were building the intuition that they had?
I think that based on the first simulation that we saw,
Yes.
We can see that rho plus, which is on the y-axis,
Yes.
it tends to a constant. So at least in that case, or those cases that we saw, that it happens that the rho plus dt goes to 0 indeed at high t. So that's why I imagine that this approximation would be good.
Would be good where?
Could you please open the plots? It's just the rho plus as a function of t.
Sorry?
Before, slide before that. In this case, in this case for high t's, we have d rho plus, that it's the y, rho plus the y-axis.
Rho plus is the y-axis, yes.
At high t's,
At high times,
yeah,
Yes.
exactly, at high times,
yes.
d rho plus dt goes to 0. So
D rho plus,
dt, the derivative of those curves
yes,
go
yes,
to 0.
yes,
And that's the only point where they go to 0
yes,
in these points.
yes.
So that's why my intuition was that these calculations, these estimatives, they will be good.
But I think we are losing something. So what I'm showing you here is just, so here what I have is b 0.1, well, 1 divided by b 0.175. What I'm showing you here is for 0.175, 0.79. So this red point is this value, right? So the fact that this has a stationary state, fine. This has a stationary state, fine. But my question is, actually, I think there is a way of doing this. Okay, you are really challenging my drawing skills. Let's try to do it. This is a very important point conceptually, so I want you to try to think about it a little bit at least. So this is time, and this is rho plus. So this is basically the plot that we had before. For the numerical simulations, what I was showing you, this is 1 and this is 0. When I was starting here, I had, this is 0.79, or wherever value we had. What I was showing you is that for different initial densities, my curves all go to the same value. This one. If I integrate numerically, that's something I could have done, I didn't think. If I had integrated this numerically and I put it here, what I'm telling you is that it will have some value, some behavior, that would always be, well, this is 1. Still the same behavior, still going to a fixed point, but a higher one. I don't know, 181 or 87. Always a higher one. And this is what this curve is telling me. What this plot is telling me is that this approximation, when I do the trajectories, it always goes to a fixed point that is higher than the numerical simulations. Yes?
It's not just because you're assuming that everyone is in contact with everyone, it's not true.
There is no contact, no? Here. I'm assuming.
The one-fixed condition
Exactly.
is leading to the.
Exactly. Why?
So each.
No, sorry. Let's Giuliani finish.
No, I guess you assume this to make the calculations.
Yes?
In your simulations, that's not true, right?
Yes, but my question is, were you expecting that my calculations would go here instead of here? You didn't have an intuition? You know what I mean? I agree with you. Assuming the well mixed gives me a different result because I'm assuming that my seeds go everywhere.
And that's not true in the simulations.
And why that approximation is giving me a higher value?
Because if you have more contacts, you have more infections, more duplications.
Exactly, because if my tree can put their seeds everywhere in the lattice, configurations, if my sick people can put sick people everywhere in the lattice, configurations like this a very simple one in which I have a group of sick people finding a group of healthy people. In my simulations, there is only one event that transmits the process.
That's it.
But here, all these can transmit the process. So, and this is the reason why I wanted to focus a little bit in this, we are learning some physics here, is because we got some questions yesterday about the topology, right? How is the topology important here? How is the dimension important here? The theory that I wrote there, the equation that I wrote there, is an approximation for a one-dimensional lattice. But for a topology in which everyone is connected to everyone, it's an exact result. So if I run my simulations, and in my neighbors, when I sample my neighbors, instead of choosing right or left, I choose any place in the lattice, because let's say I have a virus that spreads very far away, or I have seeds that go very, very far away in my savanna, then my numerical result is going to be exact when I compare it with my theory. Because I am not doing any approximation, basically. Right? Is that clear? Because this is going to be very important tomorrow. In this case, the space doesn't matter. If this is what this is what people call a fully connected network, no? So if we think of a very small system, with only 5 towns, let's say this is the spreading process that Raisa was explaining us yesterday. I know it very well. I have my 4 towns in Bahia. Well, this is not Bahia. This is my region in Spain that has very, very small towns, very few towns. This is how my one-dimensional lattice looks like, right? Every neighbor has only 2 places. But if I have connections that are like this, then I basically have the same conditions, the same spreading conditions that I have in my theory, right? Whenever I have a plus here, it can spread to this one, to this one, to this one, and so on and so forth. So this is a fully connected network, and this is a 1D regular lattice with periodic boundary conditions. Of course, in between these 2 things, there are, I don't know, complex networks where you have nodes that have a lot of connections and others that don't have so many. For instance, this is a network that we use a lot in evolutionary biology to try to study spreading processes and so on. Yes, questions? First there.
What is the intuition behind the fact that the solution and the numerical simulations are equivalent for higher values of B?
Ah, very good question. What is the intuition? Any intuition? Anyone? You have intuition or a question?
When the birth rate is really high, you always get the available sites populated. If you're to the left of the plot, you have a very large birth rate. Even if the majority of the occupied places don't have where to go, can't see the neighbors, there are so many occupied places that they are always seated. It's very likely that an unoccupied site has an occupied site right next to it. That's my intuition, at least.
Yeah, that is what is happening. No? When you have more more occupied places, the probability that empty places have occupied places is very high. No, so at the end, you are always filling the empty places. No, yeah. And then as you decrease the beta and you create spatial structures in your distribution of places, then you get more configurations like.
Yeah, I mean,
you basically get more pairs or triplets of zeros.
Yeah, I mean, because the value of B is related with the density, right?
The what, sorry?
The value of B is somehow related with the density of O because it increases the density.
The value of B, no.
proportional.
The value of B, no. But the growth term, yes. So B times rho is the growth term. That is your intuition.
Yeah, okay.
So this is what you mean.
Yeah,
B
yeah,
times
yeah,
rho.
yeah.
Yeah, but B is constant. Remember
yeah.
that is the rate at which you, I don't know, you spread viruses, so you throw seeds, so you create a meme or whatever.
No, that's okay. Thank you.
Thank you.
Just a technical question. Have you used periodic boundary conditions in your computational simulations?
Yes.
Okay, thanks.
Yeah, but periodic boundary conditions help, but they are not the solution of all the problems. Even when you have periodic boundary conditions, you have finite size effects. That's why when you want to study critical properties, you need to do finite size scaling simulations, and you need to do things more technical that I'm not going to enter into them. If you want to learn those, you can read the Marron and Dickman book. I recommended yesterday. For anything technical regarding these models, that is the book that I recommend you to read. Great. Yes.
So this wonderful technique of model and see the network can give us the idea of mechanism network, or all the phenomena are dependent of the network.
No, so I mean all the things we are looking at, they depend on the topology of the interactions, basically on the geometry of the interactions behind your dynamics. Okay. But what is interesting, let me change your question a little bit in my favor, is that some of the things we are looking at, they don't depend on the model. So if you take a model that has the same symmetries of this model, and you run it in a one-dimensional lattice, you may have similar behaviors. And that is the idea of universality class in statistical mechanics.
Thanks.
I was going to say something 3 questions ago and I forgot. Probably was not important. Good. What time is it? We started at noon, right? Great. Yeah, now I remember. Yes, perfect. It's related with this idea of this result being exact when my network is a fully connected network, when everyone is interacting with everyone. The fact that this result is exact in a given dimension allows me to calculate things like critical exponents, the existence of critical slowing down or not. So this is a theory that we can use. That is what I wanted to say, that this is exact in infinite dimensions, and if you want to analyze the behavior of a given model in an infinite dimension, in infinite dimensions, then this is a good theory and it's accurate. What is the definition of infinite dimension? This is something we were discussing yesterday. And the idea is that many of these models, they behave in different ways in 1 dimension, in 2 dimensions, in 3 dimensions, but above a given dimension, they converge to these behaviors. So that's why, assuming well-mixed interactions, assuming a well-mixed model, it's very useful because sometimes imagine that you are working with a model that has a critical dimension 2. If you want to study it in 3 dimensions, it's the same as studying in mean field, in well-mixed case, okay? That's why. But this is a bit far from what we are going to do, but I wanted to try to connect maybe with things that you already know. Perfect. So now let me introduce very, very briefly, because I don't have time to do anything, but I want to introduce you a little bit what we are going to do tomorrow. Tomorrow it's going to be a little bit, I wouldn't say technical, but we are going to use some concepts and ideas that I will need you to be awake. So if you have to choose between going to the bar today or tomorrow, please go tomorrow. So let's prepare a little bit for what we are going to do tomorrow. So we have, yes.
Does the numerical simulation give some intuition about the term Q0 plus?
About the, sorry?
The term Q0 plus.
The Q probabilities? Yeah. Yes, good point. What do you mean by parameterize Q0 plus?
I mean, to maybe drive a function or
Q0 plus?
as a function of 1 over b, for example. And then instead of using the well-mixed state, you just use this parameterization.
So you cannot call it a parameterization because it depends on time, right? It's important. Q plus 0 and Q0, 0,
Yep.
they change with time. So it's not a fixed parameter.
Yep.
But you can do something similar to what you are thinking of. But it's not a parameterization. But you can try to approximate it better, basically, using things that you know about the system. Yes, that's what we are going to do tomorrow. So let me write the equation again. Before, almost there. This was Q0 plus. Yeah, that was it. So the first thing we have learned is that saying that this is approximately equal to rho 0 is bad. It overestimates the number of individuals that I will have at the end. So of course, the honest question, or the good question that we can have now is if I can do better. And that's what we are going to try to do tomorrow. How would you try to do this approximation better? How would you try to refine this approximation?
Maybe with some non-linearity.
Non-linearity, some non-linearity. Which kind of non-linearity?
I don't know.
Good. Well, I like non-linear people. Any idea? Any
I would
intuition?
just try to scale it.
To scale it.
Yes.
How?
By a constant multiplying rho 0, for example.
By a constant.
Yes.
Okay. What do you win with that? You have one more parameter. If you with one more, you can draw a cow.
Maybe some
It's almost there, but it's not a parameter.
some reason between the row 0 and row plus.
Rho 0 and rho plus. Okay, that I like it a bit more. So remember that we have two constraints here. We have that rho plus rho 0 is equal to 1, and we have we all agree with this, right? So let me see if this gives you a little bit more of a hint. Q0 plus, and this is equal to minus rho plus 1 minus Q plus plus. Okay, let's use. So yes, in the back.
Earth is always next to an occupied place, then you can kind of approximate it by B.
By B?
Yeah.
Something like this? We have to be very, very careful with this. This time minus 1, and this is a probability. Have to be a little bit careful with that, because this has different dimensions. We cannot approximate a time with a probability. How many of you have solved the harmonic oscillator? What do you do when you have a second order differential equation? Sometimes. Sorry? Well, no, before that. Like, what you do that when you don't know anything? Sorry? If you have a second order one-dimensional system, you try to write that's what you mean, no? That's what you meant. So, of course, this is first order. I'm not saying that I can do this here, but all I have is the same idea. I have an equation for one variable, rho plus, that has something here that it's not a parameter. That's why I said it's not a parameter. What is this? This is another variable. How many of you would try to write an equation for this other variable? Well, now all of you, no? But I can do that, no? In principle, I have a system and I can write my equation for Q plus plus and if I am lucky, this only depends on rho plus and Q plus plus, and I solve them. And I get an idea of what you were saying, Laura. I know how Q plus plus changes with time. I don't want to disappoint any of you, but this is not going to work. It's not going to work, but, well, it's not going to work fully, let's say. It's going to help us. Because when I wrote this equation, what do you expect that is going to happen? It will couple with whom? So we would like this to couple with this, right? I have x, I have y. If x is with y and y is with x, everyone is happy. But if I have an equation for x that depends on x and y, I have an equation for y that depends on x and y and on c, then I have a problem, because I have to write an equation for c. And maybe it depends on c, x, y, and v, and so on, so on, so forth. And this is what is going to happen. If I write an equation for this, that's what we are going to do tomorrow. This person here, this term here, this probability here, it's going to depend on the probability that I take a plus with a neighbor that is a plus, and then next to it has a plus, let's say. So pair correlations are going to depend on triplets. And of course, if you write all the equations, at the end you have an equation for a full correlation system, but that's not useful. So all we did these last 2 days is to take this system of equations, and I said, I don't care about this. I truncate my infinite system of ordinary differential equations in the first one. The first one that gives me densities without any spatial correlation. But in principle, I can go a little bit farther and I can say I am going to look only at nearest neighbor correlations. And I'm going to take all these terms and I am going to approximate them by things like this and things like that, and I will have a closed system of differential equations. Two differential equations. That's why I wanted you to really understand what I did yesterday and I explained yesterday so bad. Because it's are techniques that we are going to need for the rest of the for the next 1.5 class. The last half I want to show you things that we do, so to see if any of you likes the research that we do. But this is what is important here. What is important is that at the end, all I'm doing is I am constructing a hierarchy of coupled differential equations to approximate my spatial dynamics. And then I can decide where I cut it. If I cut it in the first term, in the first equation, it's very bad. Now we'll see what happens if we go to higher orders. No? Of course, in this case, and with this I finish. In the case of a model that simple as this, I mean, I don't want to do spoilers, but I don't think it's a very big spoiler. If I tell you that maybe this black line is going to be closer to the red, no? Okay. Surprise, surprise. But remember that this model is very simple, no? When I have a model like the one with the bacterial experimental setup that I was showing you in the beginning, the well-mixed case was explaining one experimental result, that's fine, but imagine that you only have the experiments in the plate, right? In that case, you never find the biostability, right? Remember that the system was not biostable in that experiment. If you do your model and you do it well-mixed, you have biostability in your model, right? So what I'm saying is that by cutting your approximations at low orders, it's not that you will approximate the numerical simulations better, like, I don't know, this line is closer, closer, closer. This is the case in which maybe it's less important. It depends on what you want to do. If you want to really match the simulations, well, but if you want to understand the qualitative behavior here, I would be very happy actually. In most of the projects that I've worked on, I would be very happy if I get a theory that tells me that this density is a monotonically decaying function and it has a point at which it goes to 0 and it has an absorbing. I would be extremely happy if I have a theory telling me that. It's a very good one. It would be better, it would be worse if I find here, I don't know, oscillations. And my theory doesn't have oscillations, no? And that is the point, that sometimes when you go to higher orders, in accounting for spatial correlations, you recover qualitative behaviors that you find in the simulations that you don't find in your theory. And that applies to, I don't know, ecological systems, but also to, I guess, neurons in connections of neurons or disease spreading or anything. No? At the end, it's the importance of a space. Sometimes there is qualitative behaviors in your model that are only due to space, and if you neglect those in the theory, you lose it. You lose them. Okay? Questions?
Okay, so you say that the way to improve the spatial modeling with this parameter is by doing calculations, using all the tools that we know in maths and physics. But there is an intuitive way to do it, like the other parameters, like, I don't know. It's any intuitive way or only with approximations we can improve spatial modeling?
What do you mean by intuitive way?
The idea is that give my compares like a reason between one probability and the other, another parameter.
You need those things. You need those things to approximate, to improve your approximation.
Okay, so
you
then
need to be creative.
Okay.
You need to use conservations between variables and these kind of things. It's not. I don't know if I'm understanding your question, but what we are going to do is not mechanical.
Okay. Thanks.
If it were mechanical, I would give you a book and I wouldn't be, probably they wouldn't allow me to come here if it were mechanical.
Perfect, thanks.
Yeah, but I thought I thought that your question was more like if there is like things like a Feynman's diagram that allow you to draw the symmetry. No. At least not that I know. In other when the space is continuous, yes, you can apply field theories and use these kind of diagrams, and it's super fun and super interesting. Okay. But I don't know, maybe here you can use them as well. I don't know how.